right, good morning, ninth grade. I hope you guys are doing well today. As you can see, we're going to be starting a new chapter of notes today. So make sure that you clearly mark off where chapter 14 ends and where chapter 15 begins. It is a brand new, it's a brand new topic, but it still coincides with what we've talked about with electrostatics and magnetism, okay? Some of the same terms are going to show up. But we're going to look more at electricity. How does it work? Why can the lights be on? Why can Amanda work if she's plugged in? And all of those things, all right? So, electricity. All right, electrons in motion. Current electricity, which is the flow of electrons or other charged particles from one place to another. All right, electricity is either static or current. Okay, we've talked about static electricity in chapter 13, how it's stationary electricity, it's there, it has the potential to move, it's just not being moved yet, but it has all the energy there to move. Then you get current electricity. This is when electricity is in motion. Okay, the electrons are moving around, they are causing electricity to move. All right, now electrons flow from one place to another because of the attraction and repulsion between electric charges. All right, electric charges are just like magnets. They have a positive end and they have a negative end. All right, they have an area of positive attraction and an area of negative attraction. And opposites attract with electrons just like they do with magnets. So positive electrons are going to seek negative electrons and negative electrons are going to seek positive electrons, all right? And it is that vice versa relationship. Now, there are two types of current electricity. Remember, current electricity is moving electricity, okay? So two types, you have direct current or DC, and you have alternating current or AC. So DC current, or DC, I guess DC current is just repetitive, isn't it? Direct current, this is electricity that flows in one direction without reversing. The electricity does not have the ability to flip back and forth with direct current. It only has the ability to go in one direction. Versus alternating current, the electricity has the ability to flip back and forth. It can flow one direction and then be flipped back in the opposite direction, okay? So direct current is one way, and alternating current, it can go both ways. Okay, some terms that you're going to need to be familiar with if we're going to work with electricity. Well, you're going to learn about electricity anyway. We might not get to work with it so much in our current situation. But voltage, this is the force with which an electric current flows. It's determined by the difference between two charges. The more intensity electrons are forced to move with, the higher the voltage will be. So basically, the more force behind the electrons, the stronger they're being pushed, the faster they're being made to move, the more voltage you have. Think of a battery, okay? You have AA batteries, you have D-cell batteries, you have 9-volt batteries, okay? And that the letter or number, let's put it this way, the letter or number given to a battery tells you how much voltage that battery has, how much power does it have, how fast are the electrons going to be forced to move through that battery, okay? Volt is the SI unit of voltage, so if you were to be working with the math problems and you were to solve it out, volt would be the SI unit that you would tack on there at the end. And then current, this is the rate of the change flow. It is the rate of, charge flow, sorry guys. It's the rate of charge flow. It is the rate of charge flow, not the total amount of charge transferred over a period of time. So current has to do with how quickly it is being, sorry, give me a second guys. I got distracted. Mr. Maxwell came in the classroom. Start again. Current. Let's go back up. Okay. Current is the rate of the charge flow. Now, it's important to realize that it is the rate of the charge flow, not the total amount of charge transferred over a time period. So, let's break it down. Let's say for 100 watts of current are pushed through, or amperes of current, excuse me, 100 amperes of current are pushed through something, okay? Current has to do with how quickly that charge is moving in general. It doesn't have to do with what is the total number at the end of the hour, okay? So how quickly is that charge moving in general versus, okay, I know I have 100 at the end of the hour. That's not what current looks like, okay? Current does not have to deal with the end number. It deals with what is the general ability of the flow, okay? Hopefully I didn't confuse you guys with that. But ampere is the SI unit of current. Oops, my bad. Current and voltage are inversely proportional. Now we've talked about directly proportional versus inversely proportional before. What all it means if it's inversely proportional is if one goes up, the other goes down, okay? No, where's my fingers? There we go. One goes up, the other goes down. All right, so if current goes up, voltage is going down. If voltage goes up, current is going down, okay? That's all that means. And it will happen at the same rate. Let me throw that in there. It'll happen at the same rate. If current goes up 5, voltage will go down 5, and vice versa. All right, power. This is the total amount of energy used per unit of time, okay? Now, power is the total time, okay? Remember, current is the general force that's being put out. Power looks at that time frame, okay? Power deals with time. Now, it depends on both the voltage and the amount of current, so it's affected by both. And as the current increases, power will increase. The SI unit for power is the watt, and the formula here is P equals VI, meaning power is equal to voltage times current. So if you know the voltage and you know the current, you can multiply them together and get your power. The kilowatt hour. This is how electric companies charge for electricity. If you guys were here, I would take you down to the end of the gym here, and I would show you where the meters read in kilowatt hours, and that's how the electric companies charge for the amount of power we use here at the school. All right, it's based on two things: the power of the electrical current and the length of time that the device operates. This is why your parents always tell you to shut the light out if you're not in a room, or to turn something off if you're not using it, okay? It's because the meter on the side of the house, the electrical meter on the side of the house, reads how much time electrical devices were on, all right? It's also why when you get older and you're paying for your own electricity, you're going to want to shut things off when you're not using them. Okay, resistance. Now, we've talked about resistance a little bit before. We've talked about conductors and insulators, but we're going to talk about them again in relation to electricity. So, conductors, these are materials that allow electric current to flow easily. They are not hindered. They're very receptive to that electric flow. In fact, they're probably going to take it before anybody else would, anything else would. So examples of these are gold, copper, and aluminum. Insulators, these are materials that insulate objects from electric currents and don't allow them to flow easily. Examples: wood, rubber, glass. This is why electric workers wear rubber boots, okay? Because if they happen to get shocked, that rubber is going to keep them from getting shocked if there happens to be a free current somewhere. Semiconductors, these are materials that are neither good conductors nor insulators. A good example of this would be the nail that you guys used in your electromagnet last week. It's not necessarily a good conductor, but it's not necessarily a good insulator either, because you could charge it electrically if you wanted to. It just doesn't naturally take on that electric charge. Resistance. So what is resistance? Resistance is the amount a certain object hinders electron flow. The unit for this is the ohm, and we're going to talk about Ohm's law here in a little bit, and you'll understand why resistance is given his name. But it's the amount a certain object hinders electron flow. Okay, how much does this object accept or reject electrons flowing through it? Resistance can be considered electrical friction. It's just another way to look at it. There are 4 factors that affect resistance. The first is the type of material. Okay, is it a good conductor? Is it a good insulator? Is it a semiconductor? What's it dealing with here? What are you dealing with here? The diameter of the conductor, how round is it? Okay, is it very large? Is it very tiny? How much space do electrons have to flow through that? The length of the conductor, and then the temperature. Okay, joule heat, this is the energy used to overcome resistance. And what happens is it gets converted into heat. That energy that you have to overcome the initial resistance is naturally converted into heat, and so they give it the term joule heat. Superconductor, this is a material that allows current to flow through it with no resistance at all. Superconductors can be very dangerous if not used properly. And then a resistor is an electrical device designed to add resistance to a circuit. Resistors help keep systems, electrical systems, from overheating or short-circuiting or getting too hot, okay? Resistors are meant to be a good thing in the electrical world, okay? Typically we think of resistance as a bad thing, but in terms of electricity, resistance is good because it helps to keep things from overheating and blowing up in your faces. All right, Ohm's law. Ohm's law, this is the mathematical relationship between voltage, current, and resistance. A man named by the last name of Ohm dedicated his life to figuring out this relationship. He was so mesmerized by it that he spent a lot of time figuring it out. And when he figured it out, they gave his law his name. Okay. Now the formula for this is V equals IR. That means voltage is equal to current times resistance. If you know at least 2, you can figure out the other one. So if you know voltage and current, you can figure out the resistance. If you know current and resistance, you can figure out the voltage. If you know if you know voltage and resistance, you can figure out the current. There's a great little pie chart that shows this relationship, and if you guys were here, we would work with it more mathematically. I'm leery to work so much with the math while you guys are away, just because I feel like that wouldn't be very fair to you to work with the math when there isn't somebody there, to work with you hands-on with that. But it is a mathematical relationship, and it's very easily done and very easily seen. Like I said, as long as you know 2, you can figure out the other one. As voltage increases or decreases, the current increases or decreases. So if voltage goes up, current goes down. Remember, they're inversely proportional. So even with Ohm's law, when you look at it, if you notice that voltage is going up and you know resistance, then you can just automatically assume that, hey, because voltage went up, current's going to go up as well. Okay, remember they're inversely, or current's going to go, current's going to go down, not up. Misspoke on my part. If you know voltage and you know resistance, and you notice that voltage is going up, then you know that current is going to go down. Okay, and if voltage is going down and you know resistance, then you know current is going to go up. Okay. And then as the voltage is held constant, the current will increase as the resistance decreases, and vice versa. Okay, so let's say voltage is held constant the entire time. What will happen is if the resistance decreases, current will increase. Okay, and that's because less resistance, more room for the current to flow. Okay, so as resistance goes down, current goes up. And as resistance comes up, current goes down, okay? So resistance goes up, current comes down, resistance goes down, current comes up, all right? And that's where we're gonna stop for today's, this week's notes video. I hope you guys can understand what I said. Hopefully it wasn't confusing for you. It's weird for me to be teaching to an empty classroom, to a laptop. It's weird not having you guys here. But anyway, I hope you guys are doing well. I miss you all, and I'm praying for you.